In pre-calculus and algebra 2, you learned about different types of things that grow with something called exponential growth. And so examples are, for example, bacteria growth or money in a bank account that has a % interest and that sort of thing. So let's look at a very basic example. Let's say we have one bacterium, and then some amount of time later it doubles to be 2, and then it doubles again to be 4, doubles again to be 8, 16, 32, and this process continues forever. So these values are our population, we'll call it P. Now, the slope between each of these, let's say that each of these are the same time value, the slope here is 1. And the slope here is 2. And the slope here is 3. The slope, no, it's not 3, it's 4. I swear I can do math. The slope here is 8, slope here is 16. Notice that the slope, let's call it, well, it has a name, it's actually dp dt, dp dt. The slope is actually equal to the population at that point in time. Okay, and this is a characteristic of all exponential growth. Mathematically, what we can say is we can say that, in this case, the dp dt equals p, the population at any point in time. Notice that p is a function of time because it changes, it's not a constant. And for exponential growth in general, sometimes what happens is that these aren't the same, like 2, 2, 1, 1, 4, 4, etc., but that there's like a ratio between them or something. And so what we can do is we could say that's equal to RP, where R basically means there's a proportionality. So in math, we have this equation. This is what this equation means in words. The derivative on the left-hand side is, just like with related rates, the rate of change of P, population, with respect to T. So the derivative is long in words, but that's what it is. Is the equal sign, basically, is equal to, no, it's not equal to, it's directly proportional to, and that's the R. That's how the R fits into this. Directly, and you learned this in Algebra 1, but directly proportional is just a constant times the value, proportional to, and what is it proportional to? It's proportional to the population. And so what we get is that because it's the rate of change of P, that's dp dt, and then directly proportional to P is R times P, or a constant times P. This is a common differential equation, and now we're going to solve it. This is my equation, dp dt equals Rp. So we need to separate and integrate using multiplication and division to separate. So notice that the dt is going to have to get over to the other side. So I'm going to multiply both sides by dt. It's going to get rid of that. And then the p over here I need to divide both sides by p in order to get rid of it. And so my separation will be dp divided by p equals, R is constant, so it could really go anywhere. I'm going to leave it with the dt. It's going to be easier to integrate it that way. So, but now it's separated because the p values and the t values are on different sides of the equal sign. Now I'm going to integrate both sides. Now you got to remember your integration rules. Here, notice that this is a natural log because we have 1 over p dp. So this is going to be ln of the absolute value of p plus c. I'll put the c's in blue because they're constant, equals, and the integral of r dt, r is a constant, and the integral of dt is just t, so we get rt, and then plus a new constant, so we'll call this c1, we'll call this c2. Alright, cool. Let's go ahead and simplify. So I'll get ln, absolute value of p. Moving this constant to the other side, the c1 and the c2 become a new constant, so I'm going to get r t plus c3, like that. Alright, now how do I get rid of natural log? Well, the answer is I have to do e to both sides. So I'm going to do e to this whole side, parentheses, e to this whole side. The e and the ln go away, and so I get absolute value of p equals e to the rt plus C3. All right, a couple things here. You do have to remember properties of exponents. If I have addition with my exponents, what I can do is split this up into two separate exponents. I can do e to the RT times e to the C3. And the reason that I wrote this e in blue is because e is a constant and C3 is a constant, and so this term becomes a new constant. It's called C4. Boom. On the other side of the equal side, I still have my absolute value of p, like this. We're going to go ahead and go to a new slide. All right, so I got p equals e to the RT times C4. To get rid of the absolute value, it's very easy. All I have to do is just say plus or minus on the other side. And so I'll write it in blue because plus or minus is a constant, essentially. It's plus or minus 1 if you want to think about it that way. So I get plus or minus C4 e to the RT. And then plus or minus a constant is just going to be a new constant, so we'll call this C5. So I get P equals C5 e to the RT. All right, and then really this P is a function of t, so we can call it P of t, and then is equal to, now, here's the cool part. C5 is a constant, and essentially what this means is that at t equals 0, the population at 0 is going to be equal to C5 because this whole thing is 1 when you plug in t equals 0. And so when you see this normally, this C5 is usually written as like the initial population, or like P sub 0. And so I can write that here, and so we get that P of t equals P sub 0 e to the RT. And right now you should be very happy because, hey, it's PERT. Look at that. It's PERT. It's the exponential growth formula that you learned in algebra and pre-calculus. And this is where it comes from. It comes from the differential equation that the rate of change of a population with respect to t is directly proportional to that population. That's why this is such an important differential equation, and it shows up everywhere. As you know, this has lots of practical applications. So that's a cool way to show how calculus is actually useful. We can solve differential equations and get results that we know are true.